Welcome to this video. And in this video, we introduce the concept of nonlinear systems control. Nonlinear systems control. Linear systems have been defined as systems that obey the principles of superposition and proportionality. And therefore, nonlinear systems are systems which do not obey the principles of proportionality and superposition. By principle of proportionality, we mean that if an input x1 produces an output y1, then an input alpha x1 will produce an output alpha y1. And this is the concept of proportionality. By principle of superposition, if you have an input x1 causing an alpha y1 and an input x2 causing an output y2, then the inputs changes to alpha x1, the inputs changes to alpha x1 and beta x2. If the inputs changes to alpha x1 plus beta x2, then this would cause an output alpha y1 plus beta y2. In other words, a change in the input x1 will not affect y2, and a change in the input x2 will not change the output y1. And this, if this happens, then this is the concept of superposition when looked from a point of control systems. And therefore, nonlinear systems will not obey the principle of superposition as well as the principle of proportionality. Nonlinear systems also exhibit unique kind of behavior or properties, and therefore we look at the unique properties of nonlinear systems. The first such a property is what we call multiple equilibrium points. Multiple equilibrium points. Nonlinear systems exhibit multiple equilibrium points, where an equilibrium point is a point at which the states of the system remains constant. In other words, the states of the system remain unchanged at the equilibrium point of any given system. Linear system would have equilibrium points, but only one equilibrium point. But nonlinear system can have more than one such an equilibrium point, or a point where the states of the system remain constant. The second kind of a characteristic or a property that is unique to nonlinear system is what we call limit cycles. Limit cycles are oscillations of fixed amplitude and fixed period without the presence of an external excitation. And nonlinear systems would exhibit such kind of a behavior or oscillations of fixed amplitude and fixed period, even in the absence of an external excitation. And this mainly depends on the initial conditions of the system, and it's a unique feature of nonlinear system. A third feature is what we call bifurcation. Bifurcation. The change in the qualitative behavior of a nonlinear system, change in qualitative behavior of a nonlinear system. For example, changes in the number of equilibrium points, changes in the stability at the equilibrium point due to parameter change in the system is what we call bifurcation. And therefore, there are times when the nonlinear system will experience some change in its qualitative behavior. For example, when the system is stable at the equilibrium point, and then there is a change in the system parameters, the system could turn into an unstable system. And that change in the qualitative behavior of the system due to changes in the system parameters is what we call bifurcation, a unique property of the nonlinear system. The fourth property is what we call chaos. Now, small changes in the initial condition result in large and often unpredictable changes in the system's output. In other words, when the system experiences some small changes in the initial conditions, then these small changes in the initial conditions result in unpredictable and large changes in the system's output. And that condition is called chaos, a property also of nonlinear system. Lastly, the last property, which is a property of nonlinear system, is what we call finite escape time. Finite escape time. This is the situation where the state of an unstable nonlinear system can go to infinity in finite time. That means you have the state of a nonlinear system being unstable, and then within finite time, that state goes to infinity. And that condition is called finite escape time, a property of nonlinear systems. We look at the categories of nonlinear systems. Nonlinear systems can be classified into two main categories. The first category is of what we call the inherent or the natural nonlinearities. The inherent or the natural nonlinearities. And these are nonlinearities that occur naturally in the system, and they're not introduced into the system by the design engineer. So they naturally occur in the system, and they've got nothing to do with the design engineer. A good example of such a nonlinearity that occurs naturally in the system is saturation. Saturation is a nonlinearity experienced mostly in amplifier systems, where even as you subject the system to a change in input, then the output remains constant. Saturation, if we plot it on an axis of input to output, initially with increasing input, the output of the system will be increasing linearly. And then at some point, even as you increase the input, the output remains constant. And this is a feature or a form of nonlinearity that is notable in nonlinear systems, especially amplifier networks, and it is a condition that is inherent or naturally occurring in the given system. Other types of nonlinearities which are naturally occurring are things like the dead zone. The dead zone. Dead zone is sketched in terms of the input and output. Even as we increase the input, the output remains zero up to some point until a point where the output increases linearly with the input. And such a nonlinearity is called dead zone, seen mostly in semiconductor devices and also in amplifier networks. Other types of nonlinearities which are of inherent or the naturally occurring type are the backlash. This is mostly seen in geared systems. Where if you are to sketch the nonlinearity, at some point, the output would increase linearly with the input, remains constant, decrease linearly, and also increase or remains constant. And this kind of a nonlinearity is seen in geared system, and it is a form of naturally occurring or the inherent type of a nonlinearity. The second category is the artificial or the intentional nonlinearities. And these are the kind of nonlinearities which are introduced by the systems designer to achieve certain objectives out of the control system. And therefore, they will be intentionally introduced by the systems designer to achieve certain control aspects. A good example is the two-position relay, which if we can sketch the two-position relay as an input-output characteristic to look like this. It is the output grows suddenly at the input being 0 and then remains constant for all other values of the input. Such a characteristic is what we call the two-position relay, and it is an artificially or an intentionally introduced nonlinearity, especially in switching systems where we have the relay systems being used as switches. Those are the two types of nonlinearities, or the two categories of nonlinearities that we have: the naturally occurring and the artificially introduced nonlinearities. Next, we look at the concept of equilibrium points as refers to nonlinear systems. Equilibrium points. We've defined equilibrium points as the points where the system states remain constant or they remain unchanged. If we have our system defined by the state equation, x derivative is equals to a function of x of t and time. And of course, this is an autonomous system where the external excitation is 0. And we define the vector x as a vector consisting of x1, x2, all the way to xn. Then the system's equilibrium is going to be achieved where the state of the system is a constant. At that point, if the state is constant, then the derivative of the state will be equal to 0. And therefore, given the state equation of a nonlinear system, the state equation of an autonomous nonlinear system, to determine the equilibrium points of that system, then we need to equate the state equation to be 0, since at equilibrium, the states are constant, and at that point, the derivative of the state will be equal to 0. And therefore, to determine the states or the equilibrium point of a nonlinear system, we equate the state equation to 0, and by so we solve for the values of the states. We can take an example and put this into perspective. Suppose we have a system defined by the state equation, x1 derivative, x2 derivative is equals to -1, 2, 1, -1, x1, x of 2, of course, functions of time. If our system is defined by the state equation, we are to determine the equilibrium states of the system described by the state equation. From this, we can write our equation as x1 derivative is negative x1 plus 2x2. And x2 derivative is equals to x1 minus x2. At the equilibrium point of the nonlinearity or the nonlinear system, then we'd have negative x1 plus 2x2 to be equal to 0, and also x1 minus x2 to be equal to 0. If we add the 2, then we notice that x2 will be equal to 0. X2 will be equal to 0. At that point again, you notice that using the second equation, our x1 will be equal to x2, again, which will be equal to 0. And therefore, the point 0, 0 is an equilibrium point for our given system. And you can see this is the state equation of a linear time invariant system. This is already linear and has an equilibrium point at the point 0, 0, or the point at which the states of the system remain constant or they are unchanged. And therefore, the point 0, 0 is the equilibrium point of our nonlinear system. We can extend our discussion to the concept of linearization of nonlinear system. Linearization of nonlinear system. Again, suppose our system is defined by the state equation. X of t derivative is a function of x of t and u of t, where x of t, of course, is a vector representing x1 all the way to xn. So you can have this written as x1 derivative is a function f1 of x of t and u of t, sorry. X of 2 derivative is a function f2 of x of t and u of t, all the way up to xn derivative of t is a function fn of x of t and u of t. The system can have its output equation defined by y of t is a function g of x of t and u of t, which again represents the vector y1 of t to be a function g1 x of t in the u of t, y2 of t a function g2 of x of t and u of t, all the way up to ym, if there are m outputs, ym of t is a function gm of x of t and u of t. So if our function is defined by the system, or our system is defined by the state equation, x of t derivative is a function of x of t, where x of t is the vector x1 to xn, and y of t is our output equation defined by y of t is a function g of x of t, u of t, again, where y of t represents the vector y1 to ym. We can linearize the nonlinear system and obtain the linearized model of the system as follows. So the linearized state equation will be the small values of x derivative will be a matrix A multiplied by the small values of x plus a matrix B multiplied by the small values of u. And our output equation will be the small values of y is C small values of x plus D small values of u. And this is the linearized model of the nonlinear system. And the only determination of the only values we need to determine are the matrices A, B, C, and D based on the nonlinear model equation of our given system. Let's define the values of the matrices A, B, C, and D when we are transforming the nonlinear system into a non-linearized model. The matrix A is obtained by getting the partial derivative of the function x, a function of x of t, u of t, as a derivative of the states x. If we are differentiating f as a function or f with respect to x, then that means our matrix A would be the function f1 with respect to x1, the function f2 with respect to x1, all the way, sorry, the function f1 with respect to x2, all the way to the partial derivative of f1 with respect to xn, partial derivative of f2 with respect to x1, partial derivative of f2 with respect to x2, all the way to partial derivative of f2 with respect to xn. And we do these all the way up to the partial derivative of fn with respect to x1, fn with respect to x2, all the way to fn with respect to xn. And we evaluate these at the equilibrium point or equilibrium state of our given system and the equilibrium input of our system. And if we achieve these, then we obtain the transformation matrix A. The matrix B is obtained by differentiating partial derivative of f with respect to u. That means we can define our B as f1 with respect to u1, f1 with respect to u2, all the way to f1 with respect to ur if there are r inputs of our system, f2 with respect to u1, f2 with respect to u2, all the way to f2 with respect to ur, all the way up to fn with respect to u1, fn with respect to u2, all the way to fn with respect to ur. And of course, we obtain the partial derivatives at the equilibrium point at input of our given system. The matrix C is obtained by the partial derivative of f of our function g, partial derivative of our function g with respect to x, and our matrix D is obtained as the partial derivative of g with respect to u. And following the same procedures, then we can get all the partial derivatives of g with respect to x1 all the way to xn, and partial derivatives of g with respect to u1 all the way to ur to determine our matrices C and D. And through that, we obtain the linearized model of the nonlinear system. Let's put this into perspective in form of an example. Suppose you have a system defined by the differential equation y derivative is equals to 1 minus u squared over y squared. This is a nonlinear system defined by y derivative is 1 minus u squared over y squared, where y is the output of the system. We are to carry out the following. One, we determine the nonlinear state space model for the system. And by so, we take the states x1 to be y and x2 to be y derivative in our process of determining the state space model of the nonlinear system. Number two, we determine the linearized model of the nonlinear system state space model about the equilibrium point defined by x1 is equals to 1 and x2 is equals to 0. And at that point, the equilibrium input is u is equals to 1. So we determine the linearized model of the system about the equilibrium point 1, 0, and at that point, our input is equals to 1. The solution of our question, we will follow the following procedure. One, we want to determine the nonlinear system spaceless model, where our y derivative is defined by 1 minus u squared over y squared. We take the states x1 to be y, and therefore x1 derivative will be y derivative, which is x2. x2 is equals to y derivative. x2 is y derivative, and therefore x2 derivative will be y double derivative from this, which will be equal to 1 minus u squared over y squared, but y squared is our x1, therefore x1 squared. And therefore, we can write the nonlinear space model as x1 derivative, x2 derivative is equal to the function, the matrix A, which is 0, 1, or we can write this as just x2. Just write this as x2, so x1 derivative to x2, and x2 derivative to the 1 x1. This becomes the nonlinear. We would wish to linearize this model. We would wish to obtain the linearized model of system space, and therefore, number 2 is the linearized model. Our x1 derivative is equal to x, and from this you notice our function f1 is 2. X2 derivative is 1 minus u squared over x1 squared, and therefore our function f2 is 1 minus u squared over x1 squared. To determine the matrix A, we obtain the partial derivative of x1 with respect to x1, partial derivative of f1 with respect to x2, partial derivative of f2 with respect to x1, and partial derivative of x2 with respect to x2, and of course at the equilibrium point. And at the equilibrium point, we say x1 is equal to 1, x2 is equal to 1. Partial derivative of f with respect to f1 with respect to x is 0. f1 with respect to x2 is 1. We differentiate this with respect to x2. f2 with respect to x1 will be negative u squared 2 over x1 cube, and f2 with respect to x2 is 0, which at the equilibrium point u will be 1, x1 is 1, and therefore this will be 0, 1, negative 2. Our matrix B is the derivative of f1 with respect to u and f2 with respect to u about the equilibrium point, which will give us f1 with respect to u is 0, f2 with respect to u is f2 with respect to u will give us minus 2u over x1 squared, which will be equal to, at the equilibrium point, u is 1, and our x1 is also 1, this will be 0, negative 2. That's our matrix B, from which we can now write the state equation of the linearized model as x1 derivative, x2 derivative, x2 derivative will be equal to the matrix A, where the matrix A is 0, 1, 2, 0, x1, x2, plus the matrix B, which is 0, negative 2. Our output equation can be written as follows. our x1 is equals to y. That means if you make y the subject of the formula, y will be equal to 1, 0, x1, x2. And this becomes our linearized model of the state equation. Finally, we look at stability of the linearized model. Stability of the linearized model. Stability of a nonlinear system can only be discussed at its linearized model. That means we talk of stability of the system at its equilibrium point. To determine the stability of the system's linearized model, then we need to determine the eigenvalues of the matrix A. We determine the eigenvalues of A. And if the eigenvalues of the matrix A fall on the left half of the S-plane, if they fall on the left half of the plane, S-plane, then the system is considered to be stable. If one of them, at least one, falls on the right, at least one eigenvalue falls to the right of the half plane, with all the others falling to the left, then the system is unstable. Then finally, if any of the eigenvalues falls on the imaginary axis, if any of the eigenvalues falls on the imaginary axis, but there is no eigenvalue falling to the right of the S-plane, then the system's stability cannot be determined. In other words, we cannot conclude on the system's stability. And therefore, the stability of the linearized model will be determined by evaluating the eigenvalues of the matrix A. If all the eigenvalues fall to the left half of the S-plane, then that system is considered to be stable. If any of them falls to the right, while all the others fall to the left of the half plane, then that system is unstable. And finally, if any of the eigenvalues fall on the imaginary axis, and there is no eigenvalue falling to the right of the S-plane, then we cannot conclude on the stability of our given system. Let's put this into perspective and determine the stability of our linearized model of the nonlinear system about the equilibrium point. So our matrix A is the matrix 0, 1, 2, 0. And therefore, we determine the eigenvalues of the matrix A. The eigenvalues of the matrix A will be determined from lambda I minus A determinant is equals to 0, which will give us lambda -1 minus 2 lambda determinant is equals to 0, from which we get our lambda squared minus 2 will be equal to 0. Lambda squared will be equal to 2, and our lambda will be plus or minus the square root of 2. You notice from this, then, if you are to sketch the location of our eigenvalues, one of the eigenvalues would fall to the right at -√2, and one to the right at √2. So one to the left at -√2, and one to the right at √2. Of course, this is the imaginary, this is the real axis, and this is the imaginary axis. So you notice that one of the roots is falling to the right half of the S-plane, and therefore this system will be unstable. Since the presence of any eigenvalue to the right of the S-plane will make our system to be unstable, and therefore the stability of our system at the equilibrium point 1, 0, the stability of the system at the equilibrium point 1, 0 is an unstable equilibrium point for our given system. And That is the concept of stability, as refers to the linearized model of a nonlinear system. And that is the end of my introduction to nonlinear systems, where we are going to look at the definition of the nonlinear systems, the unique properties of nonlinear system, the determination of the equilibrium point for nonlinear system, linearization of the nonlinear system, or the determination of the linearized model of the nonlinear system, and the stability of the linearized model about the equilibrium point. Otherwise, thank you so much for watching this video, and that is the end of my presentation.